The objective of this project is to design, manufacture and optimize, where possible, a wing semi-span from foam board. Multiple spar cross-section designs are possible, each providing specific benefits and drawbacks. The I-beam design is good at resisting torsion for a given mass of material due to its high second moment of area, a geometric property measuring how a shape's points are distributed with respect to an arbitrary axis, and the circular cross-section is optimal for resisting torsion due to its high second polar moment of area. The universal shape for resisting both is a rectangular cross-section. Importing all the data of the design specifications, material properties, cross-section design, and so on allowed calculations to become instantaneous and free of human error. This meant many design ideas could instantly be ruled out as calculations showed, for example, that they were too weak or didn't fit in the aerofoil. From actual lab testing, we were able to calculate a Young's modulus, approximately 254 megapascals, different to the given one, allowing us to perform more accurate calculations. Bending tests on SolidWorks show on the maximum stress occur at the root of the spar, and from Excel we knew how much to reinforce by. The top is in tension and the bottom is in compression. Where early designs failed most often, more testing showed the maximum deflection is at the tip of the wing, as we assume our load acts as a point at the tip, so moments increase linearly from 0 at the tip to max at the root. During the lab testing, our design evolved from a basic foam board cuboid into a structure that was closer to meeting the design brief with careful considerations made. Part of the manufacturing process, we needed to meet the design specifications whilst optimizing weight, and on an industrial scale, cost and difficulty to produce would need to be considered. An ideal design concept is to have a tapered spar with more material at the root and less at the tip to reinforce stresses where needed and save material elsewhere. With a linear decrease from 20mm at the root to 5mm at the tip, however, in practice we couldn't produce this from foam board, so we had to make steps from multiple layers and glue them together. The early tests of the spar were generally good at resisting torsion due to this rectangular shape, so our main focus was on meeting the bending moment specifications. Improvements we could make would be to reattempt the build with an improved concept of the manufacturing process, for example, cutting holes in the centerline sidewalls to reduce mass to compensate for actual mass being slightly higher than theoretical due to glue and other manufacturing features, and higher build quality such as measuring with square edges and becoming more proficient with the heat gun.